So good afternoon, everyone. My name is Rahul Sequeira, and I'm the simulation engineer here at LaunchTech. Today, I'll be presenting a webinar based on the calibration of materials using Abaqus. For those who were not able to attend the webinar, the video will be made online on our YouTube and LinkedIn pages, so I recommend to follow or subscribe to those pages. If you have any questions during the course of the webinar, then please feel free to drop them at the comments panel. Moreover, I've noticed there are some major experts in Abaqus that are also attending. So I would like to apologize if you feel like the webinar is too basic in some ways, because I just want to introduce a droplet to an ocean of what calibration of materials can be done using Abaqus. And I hope you all find the webinar very insightful. I will firstly introduce ourselves as LaunchTech and what we do here in the Middle East, alongside an overview of SIMULIA portfolio. I will then introduce you about material calibration of both the metals and elastomers. And then I will follow that with the live demo. After the demo, I will then introduce some advanced topics like subroutines and the use of Isight. And then I will conclude the webinar with the Q&A session. A bit about ourselves. LaunchTech is a UAE-based engineering company that specializes in both mechanical simulations and FEA modeling. We have a very good partnership with our developer Dassault system, as we are not only the official distributor, but their development and service partner here in the Middle East region. Some of the services we do alongside the service distribution also involves around technical consultancy, some software training, technical training for those who require it, and then we complement those technical trainings with certifications as well. Basically, the SIMULIA portfolio includes a number of different simulation types. For example, Abaqus is well known as an FEA. We have also some optimization, fatigue analysis, CFD, and electromagnetics. But for today, as I will be giving just a topic on one of the capabilities of what the Abaqus FEA can do, and that is on the material calibration of materials. So let's move forward to why we need calibration and the motivation behind it. But before that, I'd like to share with you a poll on understanding the proficiencies of your level of in Abaqus, especially with the proficiency of calibration. All right, so let's move on with the webinar. So what is material calibration? So it's actually the process of just adjusting your numerical or physical modeling parameters for the purpose of either improving or agreeing with the experimental data. Based on the above definition, we can also say it is also a process of adjusting material parameters or the coefficients for improving the agreements of experimental data. In other words, what I'm trying to say is that material calibration involves reverse engineering so that the material coefficients or the parameters of the available test data can be done. Sorry, my bad. Yes. So how can materials be modeled in any simulation? It's actually a challenge because they can, for linear elastic, it can be simple with the tension test where the data can be provided in order to find the Young's modulus and the Poisson's ratio. However, when we move into the non-linear elasticity of materials, like for example with elastomers, they require more complex sets of test data to determine their material coefficients, and that becomes time-consuming and expensive. So generally, we have three ways of doing it, either through curve fitting methods in Excel. We could use Abaqus or its plugins to do calibrations, or we could even go with an advanced method of using automation with Abaqus and Isight. When we talk about material behaviors, there are actually different materials that behave according to their structure. So sometimes most metals behave with reasonable ductility under elastic plastic behaviors. because of their uniform structure. When we think about glasses, they have actually high strength of elasticity, but very poor plasticity, and that's why they damage easily once you reach that yield point. When we think about polymers, they actually behave under hyperelasticity due to their long chain structures. So there are some common questions when we model materials in Abaqus. What is the best way to model a material like nylon or stainless steel? What are the additional parameters you need to capture your material model, whether you have elasticity, time dependence, or whether you require temperature included into your model? And what tests should I perform for the calibration? So there are many more. There is actually no simple answer, and it actually depends on your application. I also want you to know that Abaqus gives you the tools, but it's actually the knowledge of the tools necessary in order to do those simulations accurately. If you do not know if you do not know the knowledge of the material data, then there is actually no guarantee of a successful outcome. So what is material calibration? When we calibrate a material, it's actually the process of deriving the Abaqus material behaviors from your material test data. In default, the Abaqus actually calibrates using elastic plastic, or hyperelastic properties. It's basically taking the test data and using Abaqus to convert them to material or behavior properties. You can even do them using plugins which are available in Abaqus CAE. However, I will just be explaining for now how you do it using the general 3 steps. The first steps obviously involves creating a data set where you actually right click the calibration and create the material. You then import the data in the form of stress strain curves, and then you could actually ask Abaqus to declare it in the form of stress strains or force displacements, or even axial or transverse strains if you have, for example, if you have to model Poisson's ratio. Abaqus also gives you the option to model the sets in the form of nominal or true engineering stresses. You then have the option to process the data, as it's important to smoothen up coarse data. So Abaqus gives you the option to either convert the data or scale the data. You could even smooth and truncate if you require. Lastly, once the material has been declared, you could then choose the correct yield points, the ultimate points, and then from those values you can get the plastic points. When you talk about hyperelasticity, then you need to also include effects like the Mullins effect into your data series. So I'll be talking about the calibration of metals and elastomers, and I will first start with metals. But before that, we have a poll asking you about on usually which type of materials you would like to calibrate it or calibrate in your organizations. All right, I believe the poll is done. And I will now get on with how we typically calibrate metals. So when we think about metals, we have to think about either elasticity or plasticity. Let's take elasticity for this case. When we think about elastic materials, we know that the effects are reversible after loading and unloading. So in this point, we need to think about are our data with Young's modulus and Poisson's ratio good enough? Let's take an example for this titanium alloy, which is a Ti6Al4V, majorly used in the medical industry. I have the data here of the elastic points that I've taken from my test data in the form of uniaxial test data. From that test data, I can actually take the stress strain curves and then find the Young's modulus. If I have the axial and transverse strain data, I can even use those data to find the Poisson's ratio. However, just note that this is only for elastic, and when we think about plastic deformations, then there are different considerations to take because the complexity increases. So when we think about metal plasticity, we know that this is a point where Hooke's law cannot be followed anymore. So when we reach plastic points, we have to think about other complexities or other equations to use in order to interpolate or extrapolate those data. And one way you could do that is by using the Holloman-Ludwig power equations. So with yield data, you should always remember Abaqus wants it in the form of true stress versus logarithmic strain. So in the case you have engineering stress and logarithmic strains or nominal ones, Abaqus gives you the option of converting them to true strains and stresses. One thing you should remember though when you calibrate using metals, you should always consider the last point to be the ultimate stress point or the ultimate tensile or compression points. Why is because once you reach necking, as you can see with the diagram in the slide, you could see that there is a divergence of results between the engineering stress, which is given in pink, and then the extensometer strain, which is given in blue. So it's always to remember to keep within the correlation points, which is until the UTS points. So when we talk about metal plasticity, there are two ways of actually modeling the direction. One is by isotropic, or when the plasticity is agreeable with with the same directions. You could do that, and with Abaqus, what Abaqus considers the last data point is then an extrapolation of the point at the same data. However, if your metal plasticity behaves differently in different directions, then you'll have to go through anisotropic metal plasticities, and those are given through the Hills potentials, for example. So how do we then describe hardening? So hardening are described with three ways, as you can see with the images below. For perfect plasticity or isotropic hardening, they can be used for applications such as car crash analysis, metal forming, or general collapse studies like monotonic loadings. With kinematic hardening or combined isotropic kinematic hardening, they can be done if you're using applications involve cyclic loadings, for example, a piston application. There are other plasticity as well, like the Johnson-Cook plasticity model, which are very well suited to model high strain rate deformation of metals. For those who would like to use more advanced hardening methods, Abaqus gives you that option in the form of user subroutines. So how can all this be done? It's by simply going through the materials model in Abaqus, going through the plasticity model, clicking the plastic parameters, and then choosing the right type of hardening you will require. So for in this case, if you see the user one, that is where you are allowed to use the user subroutine to model your materials. Now, the way you could actually take the experimental data are divided in two main functions. One is by either using the force indentation method, or the other one is by using the uniaxial or the biaxial strip method. Force indentation is where you actually indent your substrate with a considerable amount of force by the means of loading and unloading, and those data are then converted to stress strain curves when using it in Abaqus. Processing of those data are usually important to smoothen them, and then you could model the elastic plastic behavior using the material calibration options. Another method that you could use is obviously the uniaxial biaxial test data. You could actually take either the uniaxial tension or the biaxial compression, or you could take the uniaxial compression, which is the same to the biaxial tension. You could use these data then to import it within Abaqus, and then process the data obviously for smoothing or truncating the data. Once you have the correct data sets, you then can model the plastic behavior to get your yield, ultimate strength, and plastic points. As you can see with the same example I've done with the titanium alloy, you could see that I have done the calibration. I have then used the Abaqus options to find my yield points and my UTS, and from those data I can then get the plastic points to calibrate my material. Now let's move on towards elastomers. So what really are elastomers or hyperelastic materials? They are basically materials that develop large elastic strains. For example, you can think about your rubber tires or your keypad springs and seals. Now with hyperelastic materials, they're actually based on an equation which focuses on strain energy potentials. And they are, I don't want to go through a detail of them, but they're actually just divided within two parts. One is your debiatric and volumetric strain potentials. There are different methods of testing them. You could either use the Neo-Hookean or the Ogden or the Marlow. However, it's up to the user to decide, because in the end, the accurate model would give a better correlation of data with your experimental points. There are two ways of actually calibrating hyperelastic materials. One is by using the material evaluation and permanent sets. For this case, the permanent set is out of scope for the webinar since it's a very advanced topic. So we will just stick with the material evaluation option. When we look at an hyperelasticity model, let's take high density polyethylene as an example, or HDPE as we know it. In order to actually do that, we actually just have to go through the elastic and hyperelastic model. Since in this case, we don't really know the exact model that we use, we can actually just specify it as an unknown. If you know the Poisson's ratio through experimental data, then yes, you can add that. But if you do not know, then you still have the option of using a volumetric test data. In this case, since I have the uniaxial test data for HDPE, I will just add the test data for that. Then once I'm done with adding the test data, I know that the data that I provided to Abaqus might be coarse, so I smoothen it out using the smooth option. I then declare the values of the nominal stress strain curves. If you have the true stress strain curves, you can obviously use the calibration to convert them to nominal data if necessary. Once the data is of acceptable values, you then use the evaluation option, obviously keeping your minimum strains to 0 and the maximum strains to a value which you feel is appropriate, and then doing the evaluation process. Then when you do the evaluation process, Abaqus will actually give you an assessment of those data. So for example, in this case, it's seen that the Mooney-Rivlin model is actually unstable because it has negative gradients. And then it also shows that the Neo-Hookean and the Marlow model are stable. So these are acceptable models. However, we cannot really conclude with that. We still need to see a graphical representation of those. So the next slide will show you that. If you see the graphical representation, you could see that the experimental data is shown in the red points. And we now know that the Neo-Hookean and the Marlow model is actually the only stable points. But if you see the Neo-Hookean model, which is shown in the yellow points, you know that it's no way correlating with the data as shown experimentally. With that being said, you can see that the Marlow model correlates exactly with the experimental data. So for in this case, the Marlow model is an accurate model. That being said, it does not mean that the Marlow model should always be used. It depends on the application. So in this case, you need to verify the correlation between the predicted behavior of your elastomers and your experimental data. And with that, I will give you a 5 to 10 minute demo of what you can do in Abaqus to calibrate your materials. So here's my Abaqus CAE. And for my first example, I will show you of how I've done with titanium elastic, as you can see here. So firstly, I go onto my test data set. I go onto the test data, and here are my experimental values of the stress strain curves. In this case, I have given the true strain and the true stress curves because this is what Abaqus requires. And then from there, I then smoothen out the curve using the process option, which is given here. You have 4 options to do it. I prefer smoothing out the data because it's easier. It's easier to get better Young's modulus and Poisson's ratio from those values. And then here are then my smooth data curves as shown in Abaqus, as well as the table here. After you're done with that, then you need to go on to the behaviors and then define the behavior. So for in this case, I just want an elastic behavior. So if I double click it, I have the option of going with either the elastic or plastic. As I said, I want the elastic. I choose the elastic and then continue and then create my my behavior, which is shown in this window here. Since I only have the stress strain curves, I can only use the Young's modulus. The Poisson's ratio can be found using obviously the axial or transverse strain curves. So those can be done during the using another data and then finding the Poisson's ratio. And then from that, I can choose, like for example, this titanium alloy and then apply it to that material. So when I go to that titanium alloy material, I can already see that the elastic points are given according to that calibration, and the plastic points are also given according to those calibrations as well. So this is how calibration of metals can be done using Abaqus. Secondly, now if I'm interested, for example, an HDPE model. So let's go to the calibration of HDPE. I have my nominal test data results here, because the thing with the plastics is that I had it in true test data, and I do not want that. So what I do is I go onto the true test data and then I process it. I convert it into the nominal or the engineering form and then get my nominal test data. When I go into the materials option, I then can choose the mechanical, elasticity, and the hyperelastic model in this case. I then choose, in this case, I just want an isotropic, so I choose isotropic. I choose my strain energy potential to be unknown, as I right now do not know the correct strain energy potential. And I use it according to the test data. So my uniaxial test data can be seen in this chart here, as you can see here. So these are my uniaxial test data which I have given to Abaqus thanks to the calibration of the plastic points. I then right click my material and click the evaluate option. From that, I can then say that this is just the uniaxial data. I like a minimum strain of 0. And then my strain energy potentials, I prefer it being a Mooney-Rivlin or an Ogden and Marlowe as my correct model. I'll even prefer a Neo-Hookean. I press OK, and Abaqus will then start the evaluation procedure. And then from the evaluation procedure, you will get the curves and the assessment as you seen on the charts there. So I hope the live demo gave an insight of how you can actually do those calibration of metals and evaluation of hyperelasticity metals in Abaqus. Okay, so now I'll move on to the advanced topics of calibration. One way in how calibration can be succeeded is by using Isight. In this case, let's just say I have multiple test data, uniaxial, volumetric, biaxial. They're very difficult to actually do the data matching and optimization. So you could use Isight and it would give you the correct Young's modulus according to its optimization strategies. Some people might ask, why doesn't Abaqus not have a material database? Actually, Abaqus does have its own material database. It's in the materials library option. If you can find that there is an option available. The database can be populated using either Abaqus CAE or importing data using third-party applications. And the material database in Abaqus is also beneficial because we can share those between users. So for example, if you're working within a team, collaboration is possible within this material database option. For those who are also interested with fatigue analysis of materials, that also is possible. You can calibrate fatigue by using the SN curves or the strain N curves, or by using another form called the Ramberg-Osgood equations. But this is not done through Abaqus. This is run to a specialized software called FEA within our SIMULIA portfolio. And for those who require to use specialized forms of plastic hardening or plasticity, the Abaqus gives you that option by using user subroutines. Those user subroutines can be coded in the form of either C, C++, or even Fortran code. And then since Fortran is usually a preferred method of modeling those materials, there are some codes given here in the form of UMAT, VUMAT, or UHyper. For those who want direct calibration of other materials rather than just the elastic plastic, or hyperelastic, there is a support page called the knowledge base where you can get a plugin to do calibration of many materials, not only just the elastic or the inelastic. There are viscoelastic calibrations and other nitinol material behaviors you can even calibrate. So in this case, if you wish to understand a bit more about the plugins, I would ask you to take a screenshot of this slide so that you can go onto the knowledge base then and then type out this query and get the plugin from there. So I'll just give 30 seconds for you all to just screenshot it and then take notes of it if you wish. All right. So lastly, if there are clients who are looking to renew, or if there are those who wish to use Abaqus or other SIMULIA softwares, we are still running a promotion for SIMULIA 2021 softwares. In order to be eligible, you just drop us a mail so that we can evaluate your eligibility, and if you are qualified for the eligibility criteria, you will then be enabled to get those promotions. And with that, we conclude our webinar for material calibration. I hope this webinar gave you an insightful overview of what Abaqus can do in order to calibrate your materials. If you have any questions right now, the panel is open to you. However, after the webinar, if you still have further questions, you can drop us an email at contact@launchtech.ae, and we are very happy to support your queries in these cases. So I'm now opening the floor to questions. So there was one question that has been asked. So is there any provision to add ASME materials properties for CS and SS? Well, in the end, it just depends on the application. It really depends on the application and how you can do it. But yes, it is possible. I have another question asking, can you please provide more info about shape memory alloys? It's a good question, but you can do it, but you need to also consider the implementation of the shape memory alloy constitutive, and you can even use that using the subroutines UMAT or in the form of the Fortran code. So that is possible. If you wish to know more about how you can do with shape memory alloys, I would recommend you to drop an email so that we could support you with that query. So I have another question regarding the trial version available for Abaqus. There can we don't really have trial versions for Abaqus. However, for those who are in university or students who are interested in using the Abaqus, this one you are allowed to do that. So if there are university students who wish to have a student version, please contact us at LaunchTech so we can support your query in this. There's another question about, well, whether this webinar will be recorded. As I explained in the introductory slide, yes, it will be recorded, and these will be shared on our LinkedIn and YouTube pages. So I would recommend if you could follow or subscribe to these pages in order to get the recordings. Um, so another interesting question I have, can Abacus calibration plugin predict the damage parameters for elastomer materials? No, not yet. There might be a plugin you could check within the knowledge base in order to understand the damage parameters. You could drop in an email again to me, or to the email, so that I can give you relevant links to that. However, mostly for damage, it's usually done using the defaulted damage parameter options that are available within the Abacus material database. So another question I have is, how about, what do I think is the best material model for like, let's take an example, the 304 stainless steel. Well, it depends on the application again. So if you think about the NVH, the noise, vibration, and the harshness applications that are used in automotives, then yes, I think the Young's modulus and the Poisson's ratio are more than enough. However, if you're thinking about, let's just say, metal forming, casting, these applications, then you would obviously require loading situations. You would require, loading situations like either the Johnson's Cook plasticity, or other cyclic loading equations. For example, if you're thinking about piston cylinder, then yes, maybe a cyclic loading plasticity model might be required for that. In the end, with calibration, all you do is that you combine your plasticity model and the hardening model to represent a real world simulation of what might happen experimentally. So I have another question. Does Abacus include hardening soil models or any soil models? Uh, that's a good question. In terms of elasticity, you can model it, but with plasticity, it obviously you might have to use the user subroutines option to model those soil capabilities in plastic models. There might be plugins available, but I would generally recommend using the subroutines in order to model plasticity of soil based materials. There's another question. Many questions have been asked. Are there any plans to acquire Polymode? Well, I don't know as of now, and I have not actually heard about any of these news so far. So no confirmation regarding that. Regarding that. All right, so the question panel, I will conclude it now. There are many more questions that have been asked during the webinar, and I will get back to you through email after this webinar. Again, if you have many more questions in regards to the content of this webinar, specifically about calibration, please feel free to contact us at the contact@launchtech.ae. With that, I will conclude this webinar, and I again hope that you had an insightful webinar and understanding about the calibrations. Uh, so yeah, thank you everyone, and goodbye.